Hello everyone, today we are going to look on fiber fabrication. There is a wide range of methods for the fabrication of optical fiber. This can be divided into methods involving a so-called perform and methods of direct fiber production. Perform-based methods are most important, at least in the context of glass fibers, whereas direct methods like based on extrusion are common for plastic optical fibers. In this article, we will see on how performs are fabricated and methods not requiring a perform. So coming to fabrication of fiber performs. First is vapor deposition methods. Many fiber performs are fabricated with a process called modified chemical vapor deposition, MCVD or just CVD. This method was developed for silica silicon fibers in the 1970s. Here a mixture of oxygen, silicon tetrachloride and possibly other substances like germanium tetrachloride is passed through a rotating silica glass tube, which is heated from outside to approximately 1600 degrees Celsius with a flame. Chemical reactions in the gas form a fine soot of silica, which coats the inner surface of the glass tube near the burner and is sintered into a clear glass layer. The burner is continuously moved back and forth along the tube. Towards the end of the process, the gas mixture is modified to form a layer with higher refractive index, the precursor of the fiber core. Finally, the tube is collapsed by heating it to approximately 2000 degrees Celsius. Alternative vapor deposition methods are outside vapor deposition (OVD). OVD is a process where the silica soot is deposited on the surface of some target rod rather than inside a tube as with MCVD. Together with the material precursors such as silica chloride, a fuel gas such as hydrogen or methane is supplied to a burner, which is again moved along the rotating rod. After the deposition, the target rod is removed and the perform is consolidated in a furnace, which it is also purged with a drier gas for lowering the hydroxyl content. Second is vapor phase axial deposition (VAD or AVD). It is similar to OVD but uses a modified geometry where the deposition occurs at the end of the target rod. The rod is continuously pulled away from the burner and very long performs can be made. Consolidation of the material can be done in a separate zone melting process. An important difference to OVD and MCVD is that the doping profile is determined only by the burner geometry rather than by a variation of the gas mixture over time. The plasma chemical vapor deposition (PCVD) uses deposition inside a tube similar to MCVD. However, microwaves instead of a burner are used for heating the deposition region. The deposition is slow but very precise. A modified method with particularly very high is plasma impulse chemical vapor decomposition, where short microwave pulses are used. There is also plasma enhanced chemical vapor deposition, operating at atmospheric pressure with fairly high deposition rate. The performs for multimode fiber, particularly for large core fibers, are often fabricated using plasma outside deposition (POD), where an outer fluorine doped layer with depressed refractive index, later forming the fiber cladding, is made with a plasma torch. The core can be then made of pure silica without any dopant. The general advantage of vapor deposition methods is that extremely low propagation losses down to below 0.2 dB per kilometer can be achieved. Because very high purity materials can be used as contamination is avoided. In particular, silica chloride and germanium chloride are easily purified by distillation as they are liquid at room temperature, particularly when no hydrogen is present. The water content of such perfumes is very low, avoiding a strong loss peak at 1.4 micrometer, which would also affect the telecom bands. The different vapor deposition methods differ in many respects. Concerning the possible material purity, the degree, precision and flexibility of refractive index control, the mechanical strength of the fabricated fibers and the deposition efficiency and speed. Now coming to methods without vapor deposition. For materials where vapor deposition cannot be applied, the rod in tube technique is another option, where a rod of a glass with a higher refractive index is inserted into a glass tube with lower refractive index. Both can be reasonably well connected by heating, but great care is required to avoid bubbles and other disturbances. There are also casting methods where the molten core glass is poured into the cladding tube or sucked into the tube using a vacuum pump. Perfumes for photonic crystal fibers containing small holes throughout are usually fabricated by stacking capillary tubes or rods, in most cases made of pure fused silica. It is possible, of course, to introduce rare earths doped rods for active fiber method. Adapted methods for active fiber. For active fiber devices such as fiber lasers and fiber amplifiers, rare earth doped fibers are required. Here, the fiber core is doped with rare earth ions like of erbium, neutrium, yttrium, or thulium. Additional dopants can modify the refractive index, improve the solubility for rare earth ions, or modify the photosensitivity. Not all dopants can be easily incorporated with vapor decomposition methods requiring conventional materials transport. In particular, precursors for rare earth dopants usually have a too low vapor pressure. One possibility to overcome this problem is to expose the source of rare earth ions to a higher temperature. For example, a glass tube as used for MCVD may contain an additional dopant chamber or a porous silica part soaked with a rare earth salt, which is heated with an additional burner. Another common technique is solution doping, where initially a porous silica is deposited on the inner side of a hollow silica tube. This fluid is then soaked with a solution containing a rare earth salt. Later on, the perfume needs to be further processed to form a dry and compact rare earth oxide layer. An alternative technique is direct nanoparticle deposition from some aerosol. This method allows for high doping concentrations with good homogeneity and accurate control of the doping profile. Then coming to fabrication methods not involving a perform. Soft glass fibers are often fabricated with the double crucible method, where core and cladding are simultaneously drawn from the crucible. The crucible has a reservoir for the molten glass core glass, leaving a small opening at the center, and one reservoir for cladding glass. The double crucible method is older than the vapor deposition method and is still used like for soft glasses. Compared with drawing from a perform, it can be adapted more easily to different glass materials. However, it is less suitable for producing ultra pure fibers with very low losses, as it is difficult to avoid any contamination with material from the crucible. Some fibers, like plastic optical fibers, are produced in a simple extrusion process, which is similar to the double crucible method. Such fibers are interesting for applications in mass markets but do not reach top level performance. Thank you, that's all.